And what I would like to do is just tell you a little bit about the work we've been doing in Aberdeen on the effects of citric acid on the solubilisation of phosphorus in 2 of our soils. Citric acid is a triprotic acid. The structure is shown here. pK value is about 3, 5, and 6. And so you can see you can see the speciation diagram here. So the soil pH at high pHs, citric acid, 3+ state, 2+, 1+, and unionized form here. So in the soils, generally, and we're in this region here, we have the single and doubly charged species. And citric acid can affect soil P in a number of ways. It can act simply as an acidic medium, changing the pH, affecting the solubility of things like amorphous iron oxides and so on. It can also act as a competitor for organic phosphorus and phosphorus in soil in exchange mechanisms, for example, on iron oxide surfaces. And probably the third mechanism, and one that's maybe not thought about very much, it actually can remove the iron and aluminium that's actually solubilizing or holding together organic matter in an insoluble way. So if you remove the iron and aluminium from the organic matter, it would help solubilize that material. So these are the three modes of action of citric acid. And we did 3 experiments. The first one was to look at the dynamics of release of P using simple ion exchange resins. The second one was just the effect of citrate in changing the soil pH. And the third one was really the last mechanism I talked about there, the effect of using citric acid to remove the stabilizing aluminium, iron, or calcium that's holding the organic matter together, and how that might affect subsequent water solubility. And these are the 2 soils that have been used in this study, and you've heard a little bit about these 2 soils already. This one is an arable soil, and this one a kind of grassland soil. I suppose the biggest difference really is in the Olsen P value. One really is P deficient, and the other one is quite high in available P. And the pH is a unit or so apart. Both soils show inositol hexaphosphate, and that's part of the reason these actual soils were actually picked. This is the tapeworm, the arable soil. If it's blown up, you'll clearly see the inositol hexaphosphate signals indicated by the asterisks here. And the same in the Glen Sock soil, much less PI and more inositol hexaphosphate and some other forms of phosphate here. Obviously some diester and pyrophosphate as well. And this signal here is methylene diphosphonic acid. It's used the internal standard. Well, I said the first experiment was simply looking at depletion of soil with resin. And the idea here was that we would take 3.5 grams of soil, stirred in some water, and there were resin squares in the bicarbonate form in the mixture. And the idea here was to allow the resin to take up the phosphorus. Then we would add some clean resin sheet, see how much more comes out, and do this 4 times. And the idea was we would maybe deplete the inorganic pool and maybe start to see some of the organic phosphorus coming out on the resin. Well, this is for the tapeworm soil at 25 degrees here. This is the first depletion. The blue one is the total P, and the other one is blood date reactive P. And there's maybe an indication here that in the first go here, we're actually taking out some organic P on the resin. But then we see this kind of exponential decay, and we're not really removing, it looks like we're not removing organic P here. We did the reaction as well at 4 degrees to try and minimize biological activity, and we see there's a change of scale here, but a similar kind of pattern exists. And again, we're seeing inorganic P coming off. The Glen Sock soil here that had a higher percentage of inositol also showed that really we weren't extracting organic phosphorus there. So what we thought we'd do next was to actually add citrate to this system. This was just in water and soil. So these are the results for the same system, but with 10 millimolar citrate added. And the citrate solution, we adjusted the pH to be the same pH as the soil. Otherwise, we thought we'd just be looking at the effect of pH and not the effect of complexed of citrate. But what we got was some rather strange results. Rather than getting that kind of exponential decay that we saw earlier, we got very little phosphorus coming out here. And then as time went by, and this experiment takes like, it's 1 day, 2 days, 3 days, 4 days, over 4 days, we start to see the phosphorus coming out. And we thought, well, maybe this is citrate blocking the exchange sites on the resin. I'm really not quite sure just what was going on here. Same thing here at 4 degrees. So a bit of anomalous behavior there. So what we did was took some of the same soil and a very simple system here. A beaker, the soil, 3.5 grams of soil, 75 mils of citric acid solution. The pH adjusted to 6.2, and just followed the pH change with time. So the red line here is for 10 millimolar citric acid. That's the same strength as I showed you earlier. And we can see that after a number of hours, the pH suddenly increases, going up from 6.2 up to over 8. It was a bit of a surprise to see that. And the same effect with 10 times lower concentrations, 10 times lower concentrations, a little bit with the water as well. And what I suppose what we're thinking here is that because we adjusted the pH of the citric acid with sodium hydroxide, possibly the citric acid is just decomposing and effectively leaving sodium hydroxide. So a complicated kind of system. These are the concentrations of molybdate reactive phosphorus and total phosphate in the Tayport soil at the end of the experiment. So in summary, show you the pH changes. Here, this is the one that I showed you originally with the 10 millimolar citric acid. If we actually adjust it with the pH adjusted, this is for citric acid by itself, and the same for the glide soil. If we add the citric acid at soil pH, we get this big change, and same here. So this looks like, for me, some sort of microbial activity quickly affected with citric acid, but I don't really know the answer. So moving on from this, what we thought we'd do was this washing experiment. Take the soil with 30 mils, and this time we use slightly more citric acid, really to match up with the amount of iron, aluminium, phosphorus that can be taken out from this soil with ammonium oxalate. So this was to try and match up the capacity with what's taken out by acid ammonium oxalate. And the idea was here, we'd take 3 grams of the soil, wash it with citric acid, hopefully maybe the stabilizing cations were removed. We then centrifuge the mixture, analyze the supernatant by ICP, and this is some data for the Tayport soil here. This is what's been taken out by the citric acid, and the percentage here is the percentage of that taken out by ammonium oxalate. So it's much less than the ammonium oxalate. And then what we'd do, we thought, well, if we've washed out the stabilizing cations, then when we wash with water at different pHs, then we would be able to maybe see anosmic hexaphosphate and organic phosphorus coming out. So then we would resuspend the pellet, adjust the pH to somewhere between 5 and 8, and then analyze the supernatant. So these are this is the citric acid wash here for the Tayport soil and the Glen soil. So we can see as the pH goes up, this is somewhere around about 4 to 6. I'll show you the figures in a minute. You can see there's much more organic matter coming out. Again here, the brown solutions indicating a lot of organic matter. And the pHs are not exactly equivalent because if you adjust the pH of the soil, it usually takes quite a number of days to settle down. So this is the concentrations of various metals and phosphorus taken out by the water extraction at different pHs. A very sort of messy picture. I really don't understand why it's not a regular change over time. Actually trying to maybe squeeze fits that don't really exist onto these graphs. This is the Glen soil of Silverthing, a lot of scatter. Didn't actually attempt to add any lines to that. After this depletion, we thought we'd look at the residue, the pellet was left by NMR, and we can see this is the data here. The two graphs are comparing the citric acid and the hydrochloric acid. I haven't shown the original sample here, but these are the values. We see a decrease in PI, but an increase in the relative amount of esters. Same for the Glen soil, although in this case we see an actual decrease in the amount of inositol hexaphosphate or the esters being taken out here. So this soil kind of behaves a little bit differently. This is just the total budgets, just to show that we're taking out. Interestingly, this is the difference between the total P in the soil by fusion method, this by Regia, and these totals here, the amount we've looked at, are actually based on the total amount. Same for the Glen soil, they're only accounting for about 60% of the phosphorus. And the concluding message for me, it's really difficult, I think, in all these experiments, there's so many experiments we're hearing about, it's difficult to actually be sure that the effect you're looking at. And what we've started to do now is look at the decomps of citric acid using microRESP, and Courtney Giles have been doing some of that kind of stuff. Thank you.